Hey, welcome back. This unit, we've learned what a derivative is, how to find the derivative of all kinds of different functions. We've learned lots of new derivative rules, and today we're going to look at one of the practical applications of derivatives. We're going to dip our toes just slightly into physics. I want you to imagine for a second that I have a projectile, let's say a ball, and I throw it across the room. Okay? We can graph the trajectory of that ball. It's going to have some initial height, whatever point I release at, and it's going to fly through the air in sort of a predictable arc-like pattern until it hits the ground. And so this graph is measuring the height of the ball as a function of time versus the time until it hits the ground. And so what I want us to think about, not just the height of the ball, but what is the velocity of that ball? So if you think about it, the moment the ball is released from my hand, it has an initial velocity, whatever that is. But I know that at the moment when that ball reaches its apex, when it's at the very height of its travel, its velocity for just a moment is 0. So if I was to graph the velocity of this ball, I know that it would be 0 right there. And so I imagine that graph would look something like this. You have some positive initial velocity as the ball is released from my hand. It gets smaller and smaller and smaller and smaller until the ball reaches its apex. Momentarily, its velocity is 0, and then as the ball begins to fall, its velocity is negative until it hits the ground. And it's sort of a steady fall of velocity from the moment I release it until the moment it hits the ground. Now, let's think about the acceleration of the ball. Okay, what forces are acting on the ball from the moment it's released from my hand until it hits the ground? Only one force, gravity. And gravity is a negative force pulling that ball straight down. So if I were to graph the gravity, the acceleration of this ball as it travels through the air, it would look kind of like this. And so what's interesting is when we look at all three of these graphs overlaid, what pattern emerges? What do we see here? The relationship between the height, or the position, the velocity, and the acceleration of this ball. What I notice is that I go from a parabola, what looks like a quadratic, to a linear equation, to a flat constant equation. Think about that in the context of what we know about derivatives. The derivative of a quadratic is linear. The derivative of a linear is a constant. Turns out that relationship exists between position, velocity, and acceleration. Each is the derivative of the one that comes before. The derivative of position is velocity. The derivative of velocity is acceleration. The derivative of acceleration, that's a thing. The rate of change of acceleration is called the jerk. Not that that matters for this class. So now that we're armed with this knowledge that the derivative of position is velocity and the derivative of velocity is acceleration, we can answer lots of different questions about one-dimensional travel, or travel along a line. As far as some definitions, just some basic terms that we need to know. Displacement is the distance from where you started to where you finished, regardless of what happened in the middle. You take where you finished, subtract where you started, that's the displacement. The total distance traveled takes into account any twists and turns and double backs that might happen along the way. Speed is the absolute value of velocity. So if you think about our velocity graph up above, the speed graph would look like an absolute value graph. It would look like a v. And finally, we say an object is speeding up if the velocity and the acceleration have the same sign. Think about the ball being thrown through the air. When do the velocity and the acceleration have the same sign? If acceleration is always negative because of gravity. On the way down. Velocity is negative, acceleration is negative. That ball is speeding up on the way down. On the way up, it's slowing down because its velocity is positive, but its acceleration is negative. So here we go. You'll want to have your calculator handy for these questions. A particle is moving along the x-axis with position s of t. We use s for position. S of t equals t e to the sine t. Example 1, find the acceleration of the particle at time t equals 4. Well, I know that acceleration is the second derivative of position. So I know that the acceleration at time t equals 4 is the same thing as s double prime of 4. Now I can take the derivative of this function using the product rule and the chain rule, and then I can take another derivative using more product rule and more chain rule, but my calculator, and probably yours too, is capable of taking a derivative or even a second derivative of a function and plugging a value in. And so all I have to do is identify that acceleration is the second derivative of position, and then I just tell my calculator, hey, take two derivatives and plug in 4. And when I do that, my calculator gives me 1.609, and that's it. Example 2, is the particle speeding up or slowing down at time equal 4? Well, at time equal 4, I know the acceleration is positive, specifically positive 1.609. So if I knew the velocity at 4, which by the way, the velocity is the derivative of position, then I could make that determination. So again, using my calculator, I'm going to give it the position function and say, hey, take the derivative of this and plug in 4, and I get negative 0.758. So at time equal 4, the velocity is negative, the acceleration is positive. Because those two are different, the particle is slowing down at that moment. Example 3. Find the position of the particle at the time in the interval 0 to 4 when it is at rest. So when you see at rest, what that means is that it's not moving, so its velocity is 0. So to set the velocity equal to 0, first I have to find the velocity, so now I guess I really do need to take this derivative. So the velocity function, I'm combining the product rule and the chain rule here. So I've got 1 times e to the sine t plus t times e to the sine t times the derivative of sine t, which is cosine t. There's my velocity. I want to set this equal to 0. Now, because this is a calculator active problem, I can use the graph of this function to solve this. So I'm going to graph this function and then look and see where from 0 to 4 does it cross the x-axis. And it turns out that that happens at time 2.074. And that's it. So the velocity is positive until 2.074, and then it's negative until after it crosses time equal 4. So it's only going to change direction one time in the interval. So the problem is saying find the position of the particle at that specific time. So here's my recommendation. Take that value that you just solved and store it in your calculator so that you can use the exact value and plug that into your position function. So my position function evaluated at 2.074 is 4.980. And that's using the exact value, which you want to do as long as you can. Example 4 says find the displacement of the particle on the interval 0 to 4. Remember, displacement only cares about where you started and where you ended. So the position at 4 minus the position at 0 gives you your displacement. The position at 4 is 1.877. The position at 0 is 0, so my displacement is 1.877. To contrast with that, example 5 says find the total distance traveled. To find total distance traveled, the first question we have to answer is, does the particle ever turn around? Okay, I know its velocity is positive at time equals 0, but I found out in an earlier problem that at time 2.074, that it turns around and goes backwards the rest of the way. So to find the total distance traveled, I need to find the displacement from 0 to 2.074, the displacement from 2.074 to 4, the positive displacement, and then add those two values together to get the total distance traveled. So I need the absolute value of s of 2.074 minus s of 0 plus the absolute value of s of 4 minus s of 2.074. Okay. And using your calculator, these are pretty easy to find, especially if you still have that value stored from earlier. So this displacement is 4.980. This displacement is 3.103. Add them together and you get 8.084. All right, 2008 AB number 76. Notice number 76, this is a calculator problem. A particle moves along the x-axis so that at any time t greater than 0, its velocity is given by v of t equals t squared ln t plus 2. What's the acceleration of the particle at time t equals 6? Well, they gave me velocity. They asked about acceleration. What's the relationship between the two? The acceleration is the derivative of velocity. So the acceleration at time t equals 6 is the same thing as finding v prime of 6. And again, our calculator is equipped to do exactly this. You feed it this function and say, hey, calculator, take the derivative and plug in 6. It says sure thing, and it spits out 29.453. 2012 AB number 16, a particle moves along the x-axis with its position at time t given by x of t equals t minus a times t minus b, where a and b are constants and a and b are not equal. For which of the following values of t is the particle at rest? There's that word again, at rest. That means when is the velocity equal to 0? So my velocity, the derivative of my position function, I can find using the product rule. The derivative of t minus a is 1 times t minus b plus t minus a times 1. So that is 2t minus a minus b. There's your velocity function, and I want to set that equal to 0. Well, add a, add b, divide by 2. And this particle is at rest at the time a plus b over 2, which is answer choice B. And 2012 AB number 28, notice this is not a calculator problem. For t greater than 0, the position of a particle moving along the x-axis is given by x of t equals sine t minus cosine t. What is the acceleration of the particle at the point where its velocity is first equal to 0? So they gave me the position function. They want the acceleration function evaluated when the velocity function is equal to 0. So I'm going to be taking some derivatives here. So v of t, the derivative of sine t minus cosine t, is going to be cosine t minus negative sine t, so plus sine t. Okay. And I guess since we're here, we want to find out when this is equal to 0. So when is cosine t plus sine t equal to 0? Or another way to phrase that is when is sine t equal to negative cosine t? When are sine and cosine the same but opposite? This tests your unit circle knowledge. That is at t equals 3 pi over 4 in quadrant 2. So there's the time I'm looking for. I have to plug it into the acceleration, so I need to take another derivative. The derivative of cosine t plus sine t is negative sine t plus cosine t. And I want to plug in 3 pi over 4. So the acceleration evaluated at 3 pi over 4 is going to be negative sine of 3 pi over 4, so negative square root of 2 over 2, plus cosine of 3 pi over 4, so plus negative square root of 2 over 2. That's negative 2 square root of 2 over 2. 2's cancel, giving me negative square root of 2, and my answer is A. So to recap, we learned that position, velocity, and acceleration functions are all tied together by the derivative. And using the derivative, we can answer questions about position, velocity, and acceleration, but also about displacement, total distance traveled, speeding up, slowing down, etc. And that is it for our introductory unit on derivatives. If you have any questions or feedback, please feel free to share them with me. I want this channel to be as helpful for students as possible. And as always, thanks for watching.